Hello everyone, I'm Norman Wahlberger, and welcome to this preview of the Algebraic Calculus, which is going to be coming here pretty soon, and it's going to hopefully revolutionize our understanding of calculus and how we teach it. This is going to be a fully online course, and it's going to be hosted on the platform openlearning, which is an Australian framework for online education. And we'll be starting hopefully later in 2017 or early in 2018. We'll see how we go. The course is going to be called Algebraic Calculus One, and as the name suggests, it's going to be the first of at least 2 courses in calculus. So the first one is going to be like a 1-semester course, equivalent in its intent and scope to a course at a university or college. But it will be fully online with videos like this one, but also explanatory text and diagrams. So there will be additional materials. And prominently, there will be a lot of worked examples as well as homework problems. So it really will be aiming to be a complete course that you can take and you will learn calculus. There will also be a little bit of assessment. So in today's talk, I just want to introduce the basic orientation, sort of how this course is going to be different from most calculus courses, because it will be very different. And so I want to give you a little bit of an orientation about that, and we'll talk a little bit about calculus and its history too, which is sort of independent interest. So what is calculus? Well, according to Carl Boyer, who is a prominent historian of mathematics, it's the most effective instrument for scientific investigation that mathematics has ever produced. It's often called the mathematics of change. And we're going to think about it as being the child of geometry and physics. It has roots in both of these illustrious subjects and combines them in a very interesting way. So both of these subjects combine to give important motivating problems to calculus. But because we're mathematicians, probably we're going to be oriented a little bit more towards the geometry than the physics, even though we're going to be very interested in the physical applications of calculus. An important motivating problem of the calculus that comes from geometry is this one. How do you define and calculate the area enclosed by a curve? A similar kind of motivating problem coming from physics is, how do you find the mass and then the center of mass of a planar lamina, like a piece of plywood that's cut out in a certain shape? Finding the mass of such a physical object, finding the area of such a geometrical object, they are pretty close to being the same thing. Another motivating problem is, how do you define and calculate the tangent line to a curve at a point? Here's a curve in the plane, there's a point on the curve, and here we're seeing a tangent line. And the question is, first of all, how do you define what that is? And secondly, how do you actually explicitly find such a line given a curve at a point? That's a geometrical problem, and a similar or related kind of physical problem is, how do you define and calculate the velocity of a moving particle? So here's a particle that's moving in space, or perhaps in the plane, and at some particular point we might want to talk about its velocity at that particular point. So right here the particle is sort of going in that direction, which is a kind of tangential direction, so it's obviously related to this kind of question, but it's a physical analog of it. Now, these are very nice motivating questions, and they naturally fall into these 2 different parts. So these first 2 questions are really concerned with what's called the integral calculus, which is maybe more oriented towards areas or masses. And these second problems are related to what's called the differential calculus, which is more about tangents and velocities. That's a natural separation, classical separation of the calculus into sort of 2 halves, if you like. Now, no preliminary discussion of the calculus is really complete unless you address the killer application of the calculus, which is really its initial application, the initial motivation that at least led Newton to the calculus, which is how to explain the motion of the visible planets in the night sky. This is a hugely important historical problem that many civilizations, in fact, have struggled with over hundreds, maybe even thousands of years. Because if you look at the night sky, well, the stars and the moon and the sun are reasonably predictable after a while, after some careful study. But the planets are a different story. So there are 5 planets, and if you look at one of them over a long period of time, say Mars, then you think you get the hang of what it's doing night after night. But it turns out that it does sort of strange things, like it sort of doubles back and then carries on where it was going initially. So explaining what the planets are doing is a hugely important problem that has fascinated mankind for a long time. And it's really remarkable that in the 17th century, this problem was essentially solved for the first time, and solved in a really rather spectacular way. And that calculus played a pivotal role in that explanation. So the people involved there were Galileo, Copernicus, Kepler, Tycho Brahe, and prominently Newton. And the short story is that Newton's inverse square law of gravitation was then used by Newton together with the calculus to explain Kepler's laws of motion. And the story is that well, the planets have these elliptical paths around the sun, and they travel in a rather predictable way as described by Kepler's laws. And so the relative position of the, say, Earth and Mars is relatively predictable once you understand that they're moving along these ellipses. And so this retrograde motion can then be explained. Okay. So this was a hugely important application of the calculus. It really sort of the start of physics. It was really a mind-opening experience for 17th century scientists to realize that the laws of mathematics, relatively simple laws applied in the right way, could explain, the way the world really works. It was really a paradigm shift from previous more mystical explanations of the way the world is. So I think any course in calculus should at least have some angle, some view towards trying to explain this beautiful story. And we are also going to aspire to, at least in some sense, dealing with an explanation of this. It's really a beautiful story. So let me very briefly outline some of the major differences that this course is going to have with other standard calculus courses. It will be very different. Now, part of that is because I have quite different views about the foundations of mathematics than most of my mathematician colleagues. And I have strong reservations about a lot of the ways modern mathematics treats infinite processes, in particular real numbers, infinite sets, and other things like that. And so my orientation is to steer away from those problematic issues, that at least problematic for me, and try to find some safer ground, some more fundamental, more simple kind of ground that doesn't involve complexities of that kind, especially infinite kind of complexities. So what's going to happen with our course is that we're going to have integration before differentiation. That will be a kind of a novel feature. In fact, the integral calculus, we're going to sort of reestablish that in a kind of an interesting way. There will be a lot more interplay between calculus and linear algebra. Usually these subjects are quite separate, but we really are going to try to bring them together, and we'll see that linear algebra is a very powerful tool to help us understand and sort of build up calculus. So because of my orientation, we are going to steer away from so-called limits and other infinite processes. And we're going to try to replace those with generally algebraic techniques. Okay, so there's a lot more to say about that, but roughly that's what we're going to try to do. So we're going to ground ourselves, if we can, in concrete computation so that we can always make calculations to see explicitly what's really going on. And there will be a strong geometrical flavor, and will of course be motivated by physics in particular. And sort of in something in the same direction in terms of skepticism. So I'm problematic about real numbers and irrationalities. I don't think they really need to play as big a role as they currently seem to do in mathematics. So we're going to steer away from irrationalities. We're going to try to maybe avoid irrationalities, or when we do meet them, we are going to have to rethink them. So it's not going to be automatic that I'm going to assume that you know what pi is and what e is and what root 2 is. Rather, we're going to have a kind of a quotes around those things. We're going to treat them with a lot of reservation and rather carefully. Now, there will be many of you, perhaps, who do not share my skepticism with respect to infinite processes and real numbers and such. That shouldn't really bother you, because I'm not going to actually play up that part of things in this course. This course is just going to lay out calculus. But it just happens to be that I'm not going to use a lot of things that are usually invoked. So even if you don't share my skepticism, you will still find the course completely accessible and interesting. In fact, it may even be of interest to someone who does believe in infinite sets to see what one can actually do without them. You know, how far can you get if you avoid irrational numbers? If you avoid infinite processes of any kind? Probably most mathematicians' intuition is that you can't get very far. So I hope to prove that wrong. I want to show that there's actually a very rich mathematics that can be built up in a finite, completely concrete and accessible way. So my ulterior motive actually is not just to revolutionize calculus, but actually to reorient the ship of mathematics. And so what I want to do here is I really want to lay out a path that we can go down that doesn't involve these problematic things, and that allows us to proceed more firmly with our feet solidly on the ground. When one is setting up a calculus course, you have to make a lot of decisions. You have to make choices about, shall we go down this road or this road, and there are actually quite a lot of choices to make. So one way of describing the course a little bit is to tell you, which roads I'm going down when there's a fork in the road. So let me do that quickly. So in terms of, say, the difference between geometry and physics, both very important aspects of the subject, I've already mentioned that being a mathematician, especially a geometrically minded one, I'm going to steer more towards the geometric side. So this is going to be a rather geometrical course. How about the difference between static and dynamic? It's related to the first one, though. My orientation is that the dynamic aspect, that's usually an integral part of calculus, doesn't necessarily have to be phrased exactly that way. That we can capture a lot of that in a more static way. And so I am going to be a little bit more oriented towards a static point of view. In terms of the dichotomy between accessibility and rigor, I'm afraid I'm going to have to err on the side of rigor. So one of my main points here is to try to address the logical weaknesses that I currently see in calculus and analysis, which I think are actually very significant. And so I'm beholden to be as rigorous as possible. So this is going to be, in fact, I think a more rigorous course than you're probably going to find anywhere else. In terms of applied and pure, those are both very important different kinds of orientations. I'm a pure mathematician, so we are going to be sort of more towards a pure point of view. Here's another interesting dichotomy which pulls in different directions, the discrete versus the continuous. And it's probably very common for people to think that calculus is all about the continuous and other subjects are about the discrete. You may be a little bit surprised that I, of course, am very interested in the continuous, but I'm going to actually circle the discrete here just to flag the idea that we are going to try to find ways of finessing the difficulty with the continuum. Saying what the continuum actually is problematic, and there's a lot of subtlety involved in that maybe we can try to avoid by adopting something more of a discrete point of view. So of course we're interested in continuous and discrete, but maybe we're going to be more oriented towards discrete aspects than pretty well any other calculus course. The next one is a no-brainer for anybody who's watched my videos. When it comes to finite versus infinite, I have no patience whatsoever with the idea that calculus is all about infinite things. No patience with that idea at all, right? We are firmly in the camp of finite and explicit and write-downable. Absolutely. In terms of computation versus theory, well, I have a lot of sympathy with computation, but this is a theoretical course. It's a theoretical course. We're trying to lay out the actual theoretical foundations for calculus. Here's another interesting sort of fork in the road, whether we're going to be primarily concerned with functions or curves. It's not entirely clear, historically what is more important here. And most modern courses are function-oriented, but we are going to probably be on the whole a little bit more curve-oriented rather than function-oriented. Period applied. Well, we've already mentioned that one, haven't we? That's extraneous. Okay, there's another kind of hierarchy that I want to talk about in terms of the objects that we're studying. So linear functions, polynomials, power series, general functions, this is a kind of hierarchy that's acknowledged to be sort of at the center of most calculus courses. And they will play an important role, although often we'll interpret them at the level of curves, perhaps just as much as in terms of functions. But I do want to emphasize that we really are going to think of linear functions as being primary and not below our consideration. So we are going to be very interested in linear things. And you might think about the idea that if you have some curve these days, something like this, I mean, the way a modern computer thinks about this and displays it is to really break it up into a lot of little discrete parts and then to extrapolate or interpolate between those little parts linearly. Okay? So a lot of things which appear to be continuous or curved in our world are actually, when you look computationally under the bonnet, are actually sort of piecewise linear. And that's another really good reason, especially in the modern world, is to really get a solid understanding of what's happening at the linear level. That would be quite an interesting aspect of the course. Polynomials are going to be then second. So after the importance of linear functions, then come polynomials. And polynomials are going to be very important for us. Then after we've mastered linear functions and polynomials, then we will be ready to go towards power series. But probably we're not going to be able to do that in Calculus 1. That'll probably be Calculus 2 by the time we get to that stage. And what about general functions? Well, those are things that deserve quotes in my point of view. The notion of a general function is a little bit problematic, and probably we are not going to be saying too much about those. It'll turn out that if we master linear functions, polynomials, and power series, we can do pretty well any problem that needs to be done. Okay, so that's a bit of an orientation in terms of what we're interested in. And now let's turn our attention to calculus itself. Historically, what is it really about? Let's have a very fast overall view of the history of calculus from early times to modern times. So on one page, we start with Egypt and Mesopotamia, 3000 to 300 BC, where already we're interested in questions about areas and volumes, and then astronomy, motivating problems for the calculus. Then to the Greek period with Eudoxus and Archimedes, the method of exhaustion, the volume of a sphere, Archimedes' work with pi. These are precursors to the calculus and certainly have strong ingredients of the calculus in them already. Then we move to the critical 17th century with Descartes and Fermat's introduction of analytic geometry, creating a framework, planar framework for doing calculus, and already investigating properties of tangents to curves. And then the actual birth of the modern calculus with Cavalieri, Leibniz, and Newton. Now it's usually Leibniz and Newton that get all the credit, but I'm going to give a bit of credit also to Cavalieri, who came up with what I consider to be the fundamental formula in the subject, which is this one right here. There's only one formula on the page. That's the main one. So the differential and integral calculus, both born at this time, all together combining with the birth of physics due to the work of Newton. And this integral from 0 to 1 of x to the n dx equals 1 over n plus 1, certainly one of the most remarkable formulas in mathematics. And then to the 18th century, where the masters, Euler, Lagrange, Laplace, really made calculus into a major powerhouse to solve all kinds of things. Differential equations, the notion of functions becomes clarified at this time, and then a lot of widespread application to mechanics and astronomy. And then into the 19th century with Gauss, Cauchy, Weierstrass, and a sort of shifting of calculus into modern analysis, where we introduce ideas of limits, the notion of continuity is examined more carefully, complex analysis gets introduced by Cauchy, and sort of modern analysis is born around this time. And then into the 20th century where, well, all kinds of new developments, amongst which are unfortunately axiomatics, which I don't have much sympathy with, but differential geometry, so calculus on curved surfaces, quantum mechanics, important motivation coming from physics, and calculus reform in the education industry. So calculus becomes a subject for undergraduates and then eventually also for high school students. So it becomes a big business and the whole industry revolves around it. And we might also mention harmonic analysis playing a big role in that development. So those are some of the threads in a very brief history of calculus. And of course, we are now sort of at the tail end here. Calculus has already been established. It's a behemoth industry. There's hundreds of textbooks. There's really a very strong established orthodoxy about how to present calculus, although there are people who make departures. And I think the online revolution that we're seeing currently is, of course, going to contribute to that. And I'm hoping that our course is going to contribute even more to rethinking the fundamentals of calculus. So let's talk a little bit about important calculus textbooks. Historically, textbooks are the main vehicle for really educating new generations of students. The first calculus textbook is probably that of L'Hopital, written in 1696, so that's just the end of the 17th century, so calculus was still a relative newborn at that time. And his book was called Analysis of the Infinitely Small for the Understanding of Curves. What an interesting title. And here's a quote from that book, which gives you a sense of the way those 17th century people thought, and also maybe some of the problems inherent in the orientation that they had. So here's L'Hopital. The infinitely small part whereby a variable quantity is continually increased or decreased is called the differential of that quantity. Okay, so it gives us some kind of idea. Does it give us a precise idea? Then we move into the 18th century with the master, Leonhard Euler, who for sure understood calculus better than anybody previous and anybody since, okay, in my view. So monumental contributions to a lot of mathematics, but he also wrote what's arguably the most important textbook in the subject, which is Introductio in Analysum Infinitorum. Okay, it's Latin, but I think you can guess what it means. And in this textbook, which is actually quite readable, if you get an English translation, there's actually a lot of modern developments. It's here where he introduces the notion of function in a somewhat more modern sense. He talks about logarithms, circular functions like sines and cosines and tans. And he is very interested in infinite series expansions of things that Newton had already investigated and other people too, but Euler was very good at mastering the algebra of infinite series. And here's a quote from Euler where he talks about, what does the word function mean? It's an interesting question. Here's Euler. If some quantities so depend on other quantities that if the latter are changed, the former undergo change, then the former quantities are called functions of the latter. So it's in terms of quantities. If this quantity changes, then this quantity changes, then this is a function of that one. Now in the 18th century, along with all kinds of fabulous new applications of the calculus, some people started voicing objections to the foundational aspects of the subject. And prominent amongst them was George Berkeley, who was actually a bishop. And he wrote this pamphlet, wasn't a textbook really, just a sort of an essay called The Analyst, or a discourse addressed to an infidel mathematician. And it was reasonably influential in that it really alerted mathematicians to the problems. So Berkeley's point was roughly that these mathematicians are doing stuff that is really more like religion, he was a bishop, than science. And I'd like to quote from him, and I'm using this book here, which is a very nice book by C.H. Edwards called The Historical Development of the Calculus. So I'm quoting Bishop Berkeley here. So here he is. The foreign mathematicians are supposed by some, even of our own, to proceed in a manner less accurate perhaps, and geometrical yet more intelligible. Instead of flowing quantities and their fluxions, that was Newton's point of view, they consider the variable finite quantities as increasing or diminishing by the continual addition or subduction of infinitely small quantities. Instead of the velocities wherewith increments are generated, they consider the increments or decrements themselves, which they call differences, and which are supposed to be infinitely small. The difference of a line is an infinitely little line, of a plane an infinitely little plane. They suppose finite quantities to consist of parts infinitely little, and curves to be polygons, whereof the sides are infinitely little, which by the angles they make one with another determine the curvity of the line. Now, to conceive a quantity infinitely small, that is, infinitely less than any sensible or imaginable quantity, or that any the least finite magnitude is, I confess, above my capacity. And yet in the calculus differentials, which method serves to all the same intents and ends with that of fluxions, our modern analysts are not content to consider only the differences of finite quantities, they also consider the differences of those differences and the differences of the first derivatives, and so on ad infinitum. That is, they consider quantities infinitely less than the least discernible quantity, and others infinitely less than those infinitely small ones, and still others infinitely less than the preceding infinitesimals, and so on without end or limit. Okay, that was quite a long quote, but it's an important quote, and it really touches base with actually a lot of issues which are not really so far from modern calculus courses, actually. Bishop Berkeley would look at a modern calculus course and would still see a lot of examples of the kinds of things that he was objecting to more than 200 years ago. So partly as a response to his and other people's criticisms, people started to try to tighten up the subject. And one of those people was Joseph Louis Lagrange, who was a towering figure who sort of proceeded after Euler to be the main mathematician in Europe. And he wrote a book called Theorie des Fonctions Analytiques, which is a very interesting work which tries to put the calculus on an algebraic setting. He was following Euler's direction here. So Euler and Lagrange are oriented similarly. And actually I have a lot of sympathy with Lagrange's point of view. And I think he was on a very good track. And we are going to pay very close attention to that kind of thinking. Nevertheless, in the 19th century, things went off in a different direction. And that map that had been laid out by Euler and Lagrange was kind of forgotten about, and people went off in a different direction. And prominent amongst them was the great French mathematician Auguste Cauchy, who wrote a series of influential textbooks, amongst which are Cours d'analyse, Résumé de leçons sur le calculus infinitésimal, and Leçons sur le calcul différentiel. Okay. And here's a quote from Cauchy, talking about the limit, which was a concept that was being introduced at that time to try to get around the infinitely small kind of criticisms that Berkeley was making. When the successive values attributed to a variable approach indefinitely a fixed value, so as to end by differing from it by as little as one wishes, this last fixed value is called the limit of all the others. Okay, so maybe this isn't quite as precise as one might hope, but then subsequent mathematicians came along and ostensibly made things more rigorous, but whether they actually did or not is highly debatable. And in my Math Foundation series, I show actually that there are still a lot of serious difficulties with a 19th century work towards a theory of limits. Let's turn now to more 20th century works. Now, when it comes to 20th century calculus books, there are, of course, a lot. There are dozens, if not hundreds, of books. And so I think maybe a good idea is just for me to pull off the books that I have here on my shelf at home. So in terms of calculus textbooks, I have this book here, An Elementary Course of Infinitesimal Calculus by Sir Horace Lamb. And it's actually quite a nice book with lots of interesting things about it. And I think one can learn a lot from this kind of book, even though it's actually 100 years old now. Another book that I have on my shelf is this calculus book called Calculus, Introduction with Vectors and Analytic Geometry. It's by Tom Apostol. And it is a very original book and a very nice one. I have a lot of sympathy with introducing vectors and analytic geometry, and we're going to be doing that in our calculus course too. Another place where I'm following Apostol's lead is to surprisingly introduce integration before differentiation. That's not very common, but I think, and I share this with him, that that's actually probably the more natural and historical point of view. And finally, I want to point out this book here by who is probably the 20th century most important textbook writer. That was Murray R. Spiegel, who wrote for the Shomes Outline series and wrote all kinds of very important textbooks. This one's on advanced calculus, which actually we'll have something to say about advanced calculus, even though we're just working in our first course. But his approach to textbooks is very down to earth. He gives a theory in a very concise way, and then he concentrates on worked examples and very rich source of problems for students to work through. And I think it's a very nice approach that we are going to kind of emulate. So this course, Algebraic Calculus One, which will be arriving hopefully at the end of the year or thereabouts, will be aiming for a new, more rigorous and careful approach to the logical difficulties of calculus, and will present the subject in a reasonably dramatically new way. And so there will be lots of new features, and I'm hoping that it will really engage the interests of people who love mathematics and are interested in learning it well. So the course is still in preparation. There's a lot of work to be done. I'm going to be saying more about the course off and on in the months ahead, but this is a sort of a first flagging of this intention to create this course. For more information or to prepare for things, you might like to watch my Math History 9 lecture on calculus, and also Math History 25, where you talk about problems with the calculus. And of course, the Math Foundation series has all kinds of videos that talk about aspects of the calculus in terms of logical weaknesses that are currently around, that we are going to try to steer a way through in this exciting new development. So I'm going to keep you posted with more information as we develop the course. So I'll see you then. I'm Norman Wahlberger. Thanks for listening.